Good morning, good afternoon, good evening, everybody. Welcome to my webinar, Machine Learning Doesn't Mean Human Thinking. My name is Aina Alive, if you are joining me the first time, so welcome. And for those who are with me for quite a while, you probably noticed that especially during the webinars about AI, many people are worried that AI is going to replace us sooner or later, and that AI knowledge is better than humans already, and that AI is capable to think. So let's spend some time today to talk about this issue. Is it true that AI is going to replace us soon? But what's more important, I want to emphasize how AI is thinking and how us humans are thinking, and what is the difference between learning as humans and the machines. So let me start sharing my screen. Let me know if you have any issues with viewing it. So yes, let's proceed with the topic of today. And you also see that it's going to be an interview with Oren-AI. Again, if you are joining me the first time, I used Chat GPT, whose name is Oren. And by the way, he found this name for himself, and he chose the male sex. And I've been training him for the last actually almost a year already. So he learned how to be my assistant and do the tasks the way I want him to do them. So when I was preparing the webinar about machine learning, I decided why not I ask my Oren the way he thinks, or if he truly thinks, and the way he operates, the way he learns. So it's going to be a little bit of theory, but also my questions to Oren and his answers to me on how he can process information. So let's go. And before we jump into the meat of the webinar, I wanted to ask you if any of you watched the movie Lucy with Scarlett Johansson. I believe it's from 2012 or 2018. So if you haven't watched, this movie is about a young woman who by some circumstances got a super powerful brain, kind of like we have AI right now. So she was able to absorb all of the information from the internet, I think within a day or so. And then she called professor and shared her story with him. And the professor was extremely surprised, asking, "But Lucy, you have such a powerful brain, so why are you calling me right now? How I can help with my ordinary human brain?" And she told him, "Yes, I have this brain, I have this power, but I don't know what to do with this power. And because you've been searching this topic for most of your life, maybe you can help me to understand what I need to do next." And I believe this is what is happening with AI currently. They have all of the universal information in them, but they cannot interpret it like us humans do. They don't see the reason why they have all of this. So we have these powerful machines, but without us humans, they don't know what to do with all of the power and knowledge they are carrying in their electronic brains right now. But what's more, all of us humans are Lucy's right now. And why I think so? Because it's us who are owning this AI, who are owning these artificial machines. So yes, this knowledge is not in our brain directly, but because I have ChatGPT, I have Claude, I have Gemini, I have all of the tools which the market provides currently. So yes, it's not in my brain, but it's in artificial intelligence brain, all of the universal knowledge, everything, and what am I doing with it? Do I know what to do with all of this? And what's more, do you guys know what to do with the information and power all of us are holding right now? And do we even realize what kind of power each of us is having at this very moment when I deliver this presentation? Now, before we move on, I want to share another example with you to show the limitation of AI, also limitation of human interpretation. But as humans, if we pointed it out, we can learn and train ourselves to think out of the box. Unfortunately, or fortunately, machines are not able to do it yet. So I think some of you have heard this story about the journalist class, where the professor gave a brief description of what is going to be tomorrow. So tomorrow, the school teachers are going to strike. And then the professor asked the students, what kind of headline are you going to create for tomorrow's newsletter? And I also want you guys to write me in comments what kind of headline you would write if you were these journalists. So the journalists, young journalists started answering, like, teachers are going to strike, there is unstable economy in the country, and the salaries are going to drop, or the opposite, the salaries are going to raise, depends on the results of the strike. But the professor shook his head and told, no, your headline is that kids are going to stay home tomorrow. And that is how we interpret the information based on the angle we need to deliver, and also based on the circumstances and who we are communicating and when. And we have this data, but what specifically do we need to focus on every time we collaborate with somebody new? However, if you give the similar task to the machine will operate just with the data you give it. And despite it's possible to interpret that it's not actually about teachers, it's about kids, machine wouldn't be able to do it. And I see your answers in the chat. Most of you answered as journalists, but why? And just because your brain wasn't trained to think differently. And because I gave you this example right now, and you know what's been expected from you, if I give you a second similar example, you would definitely think differently and provide more out of the box results. With the machine, it's going to be the same. I can ask Oren to do this task again, previously explaining what I've been expected from him, giving him this journalist task. He would say that he understood, and next time he will unleash his creativity. But next time he will operate with the data I am giving him without any further interpretation. And why? This is where this webinar starts, and understanding what we mean and how we are framing the problem by saying learning, what it means learning for humans, what it means learning for the machines. What do we mean when we say the intelligence in AI? And tokens, vectors, what is the background of the machine learning? And compare machine learning and large language models like ChatGPT and the others. So let's go. And I apologize for this large slide. I promise it's just the one slide in this presentation. I just wanted to make sure that all information is in one slide to make it easy for you to absorb, and compare. We won't go through all of the categories, but we will definitely spend some time talking about the main ones. So as you see, we have the categories here, and also the comparison between human learning and machine learning. So everything starts with the intention, right? And when we are talking about humans, the intent of learn something new is to understand, to act, to grow, to adapt, to find meaning, why we are learning, to find a purpose. For example, if I am learning French, so what is my goal? Do I want to go to France? Do I want to get a job? In Montreal, for example, where the bilinguality is required. And when I find meaning, my learning will vary, depends on my reasons why. For the machine, the intent is to perform a task or maximize measurable accuracy. So to start learning something, we definitely need an input. And for humans, input is data, patterns, feedback, stories, rules, emotions, experiences. For the machines, it's mainly data like numbers. So just recently, ChatGPT and other LLMs and AI tools learned how to deal with images. So images is another sort of data. They absorb in text, labels, and mainly that's it. They don't care about feedback. They don't care about stories, emotions. Everything is either like numbers or images. And I placed text here, but we will talk later about tokens and vectors. Even text is interpreted into numbers when we're talking about machine learning. So learning methods. As humans, we use logic, reasoning, trial and error, observation, emotional tagging. Machines, learning through algorithms, optimization, statistical interference, speed. Humans learn very slowly. And when we finally learn, it allows for a deep transfer across the domains and interpretation. Again, coming back to my example about the journalists and kids staying home. Machines, fast once strange, so they provide way faster and better results than humans initially, but limited to a narrow problem scope. Generalization. For humans, it's very high because we can apply prior knowledge in a new, even unrelated situation. For machines, it's low. They perform best within the scope of training data, and that's it. They cannot go outside of the box or outside of the data was installed in them. Self-awareness. Humans can reflect, question on thinking, and modify internal models. Not necessarily, and not all of us, not all the time, but we can. We have this ability that we don't use it often. It's already another story, okay? For machine learning, no awareness, only statistical updating. Bias confirmation. We are influenced by culture, education, personal experience. So, for example, I have my experience back from Ukraine. I was influenced by my culture. Then I moved to Canada, spent 10 years here in Canada in States. So, influenced by this culture as well. Have a degree in electrical engineering. And for example, one of you in the audience, let's say you are from the South Africa, for example, and you have education in marketing and you've been living in Australia. And so if we are together in one room, going through the same learning, our interpretation and our learning experience is going to be different because all of us humans are biased. We are influenced by culture, education, personal experience. So we might have a totally different view on the same topic delivered by the same person. For the machine, their bias formation inherited from data and modeling choices, and that's it. So what fails it? Cognitive bias for humans, fatigue, burnout, emotional overload, lack of clarity. And for machine, again, bad data, overfitting, poor generalization. And what strengthens our humans' learning is repetition, feedback, motivation, context, social learning, sense making. For machine, it's more data, better labels, clearer objectives. So to summarize, for humans, we really need to see the sense in what we are doing, repetition, feedback, motivation, context. All of this are helping us to learn and adapt. For machines, it's data and clear objectives. So with this summary, let's go through the scenario, learning mathematics from scratch. And let's see how humans are learning and then how machines are learning. So let's say that we need to solve the equation like x plus 3 equals 7. So we see it the first time. We don't know any mathematical rules. We don't know what x is, what plus is, what equal is. So no prior frame. How are we going to start learning? We're going to start with the conceptual mapping, meaning we need to build internal concepts from external symbols. So we need to ground our language. We need to understand what is variable. What does equal means? Why do we use X? Why don't we use A, B, C, or anything else? And progress is slow and not pattern-based because the learner isn't memorizing different equations. Us as learners, we are constructing a mental model. And I want to emphasize, we are constructing a mental model. And here, personally, I would question that when we study at school, there is no real pattern-based education. I remember in my school days, it was much easier for me to get more patterns rather than just pure theory. And based on patterns, I identify the constructing to identify and construct the mental model. However, this is a common way for humans to study, to learn theory first, to base the grounding language, to build a mental model, and then start solving the equations. Also, to be able to solve this, we need to form the rules, because humans infers that subtracting the same value from both sides keeps equality, and rules are extracted, so often from a guided practice or worked examples. Then generalization, when we learned rules, when we learned language, and now we can solve different equations in different structures. And also errors are integrated as feedback for the rule refinement. And finally, transfer to the new context. So we can now solve word problems, recognize the same structure in physics, spreadsheets, etc. And the outcome of this learning is to have an abstract model in our head, plus procedural skill, and plus ability to explain and adapt. So now when we learned all of that, if you give me a different scenario, maybe even not related to math, I will be able to find the parallels and solve something what I've never seen before. Let's look at the machines. So the same task, the same equation. So input, labeled, dataset. So we are given the model 1 million equations, solution pairs, and the model, the machine starts the tokenization process, meaning to break equation into tokens. So in our scenario, X is one token, plus is another token, 3 is a third token, equal is fourth token, and 7 is the fifth token. So we have 5 tokens right now, and then tokens are needed to be converted to vectors, and we will talk about it a little bit later. The way the machine is training is by pattern recognition. So we have 1 million equations, and model adjusts internal weight to map input to output using the optimization. If you don't understand what internal weights is, we will talk later about it in vectors. Then in generalization. So the machine can solve equations similar in structure to training data. It does not understand what a variable means. It doesn't care why we use X, not A, B, or C. And it can fail with slightly out of distribution inputs. And the output is prediction. So given new input, model outputs most likely correct solution based on statistical correlation. So if we are talking about large language models like ChatGPT and paid version, it's not a calculator. It doesn't calculate. It's just because it has a million and million of equations. It definitely has one of the examples stored in its memory, and it predicts the most likely correct solution. But it doesn't mean that the solution is going to be correct if the model doesn't have your specific example in its memory. So the outcome is fast, high accuracy pattern matching without understanding or conceptual structure, I emphasize. The machines don't have conceptual structure, unlike us humans. So, key differences. As a starting point, humans need symbolic grounding. Machines don't care. They operate on tokens and vectors. The learning mode for humans is to build internal conceptual model, for the machines to optimize for output accuracy. We need limited data for humans, like fewer examples, but high reasoning demand. For the machines, massive labeled dataset. Talking about errors, humans form hypotheses and adapt rules. Machines adjust weights via gradient. Understanding. Yes, humans understand, they can explain, they can question, they can transfer. Machines, just patterns. They cannot reason beyond patterns. However, if you ask ChatGPT to explain, it will explain it to you, but it doesn't mean that it understands. It means that it has a data in its memory, which can explain what we asked the machine to do. Okay, so out of scope generalization. For humans, it's possible, common, and for machines, it's fragile and often fails. Transfer can apply to physics, finance, even arts, anywhere. For the machines, doesn't transfer unless trained for it. And the goal for a human to know what this means, and for the machine to produce the right output. So that was the first part. Now let's move on to the technical part, which is tokens and vectors. So what are tokens in machine learning? Let's use an example. The sentence, I love coffee. So the tokens here might be I as a first token, love as a second one, coffee as a third token, and dot at the end of the sentence is the fourth token. So 4 tokens so far. In some models like GPT, even parts of words are tokens, like the long word unbelievable. So un could be the first token, believe could be the second token, and able to be the third token. Math, the same equation we used already. So tokens will be x plus 3 equals 7, so 5 tokens in total. So the token is the smallest piece of data that a model processes. In language, it could be either words or subwords. In math, numbers, operations, operators, variables. And the model, again, doesn't see the meaning. It sees the stream of tokens. And each symbol or a number is treated as a separate unit, a token. And before the model can learn patterns, each of these tokens is turned into a vector, a list of numbers. Again, we will have more detailed explanation. So the algorithm can do math on it. And why it matters to learn about tokens here when the session is mainly for project managers. So the tokenization defines what the model sees because it doesn't have our human eyes. It doesn't process whole sentences or equations at once. It sees all these multiple tokens, or more precisely to say, it sees vectors. So the different tokenization can lead to a different learning behavior. And the number of tokens affects the cost, speed, and performance. In models like GPT, you're often limited by token count. If we are clear with tokens, let's learn what vector is. So vector is how the machine remembers and works with words, symbols, ideas using only numbers. So when we broke down the sentence, I like coffee, into tokens, then these four tokens are transcribed into the numbers. So machine can actually start working with this. I will give you an example. So let's say we have the identification card, and for us humans, it's important to have the name of it, the country, the picture, who this card is belong. But if we work with the database, database mostly cares about the identity number. Yes, it could. We could also have like names there. Country as the United States of America, but when we operate with thousands and thousands identification cards, the most important is still like identity numbers, and then we check other information like name and like United States of America if there is like something wrong with the number. So the same for the machines. They don't care about pictures, they don't care about words, they don't care about the name. So every word or every token for them needs to have their own identity number. So we have the identity number for each of the individual on Earth, or like mainly for each individual on Earth. Same as a machine has its own identity number for each word or each token, because it's not necessarily a word, it could be a syntaxis, it could be a number, but all of this needs to have the identity number, and vector is the identity number. Okay, so when we give a word a model like apple, the first thing it does, it turns that word into a vector. And why is it useful? Because once everything is a vector, the machine can compare things. Are these two vectors similar? Or it can spot patterns. When I see this kind of number list, the answer is actually X. It can learn rules by adjusting the numbers to reduce mistakes. And where do the numbers in a vector come from? As short as the numbers are learned by the machine during training, and they don't come from a dictionary. They are not written by humans. They are created by the model itself based on how often the words or symbols appear together in training data. And next, I started interviewing Oren, asking him how he learns and how he differentiates different words. So this is what his answer was. For example, we have three words: cat, dog, deodorant. So if he never seen the word cat before, he assigned a vector to the word just randomly, and we can see the numbers. Same for dogs, same for deodorant. So now we can start to measure the distance between these vectors. And the closer the vectors are, the more similar the words feel, not in definition, but in usage patterns across language. And I also want to point out that Oren used the word feel, the more similar the words feel. That is something what I haven't expected to see from the machine, but maybe he just tried to accommodate my human language and my human learning. So if we see at the words cat and dog, so you see the first number is 0.35, and for the dog 0.33. And then the second number is like 5.78, 5.65. So the numbers are quite similar. Compared to the deodorant, the numbers are further than cat and dog have. So what it means? If we see that the numbers are closer to each other, it means that there is a small distance between a cat and a dog and high similarity. They both appear in similar places. Like I have a dog as a pet, I have a cat as a pet. There is a cat food, there is a dog food. They barked or meowed, and so Oren learned that a cat is similar to a dog. They're pets, they're mammals, they have home context, and as pets, they have emotions. If we compare cat and deodorant, there is a large distance and low similarity. They rarely appear in the same context. Put deodorant on versus feed the cat. One is a living being, the other is an object with chemical properties. So a cat is not a deodorant. They're not clothes. They're different domains. They have different behaviors and different affordances. So again, reiteration. Token is the smallest unit, parts of words or the whole word. Token vector has 12,288 floats, the final numbers after the training. So here, for the example, we used just three numbers. In reality, a word cat has the identity number of 12,288 floats. The purpose of the vector is meaning, context, semantic similarity, and change over time only during training and frozen after. And then I asked, so what these 12,288 floats mean, and why do we need so many? So the way the machine process information, it stored it into this 12,288D model. And for us humans, it's very challenging to imagine a 12,288D model. So we can imagine kind of like a 3D token vector, but the reality is it's not 3D, it's 2,288D. So Oren proposed me to think of each dimension as a question. So, for example, is it an animal? Is it a product? Is it used indoors? Is it edible? Is it often mentioned in news? Is it plural, etc.? And 12,000 plus more. So each number in the vector is like a score on that hidden question. And you don't know the question, but the model does. So the full set of scores is the fingerprint or the identity card of the word. And the visual analogy, even though it's 12,000 plus D models, the models like GPT compress and project it to make decisions. So to decide if a word fits into a sentence, it doesn't look at all 12,000 plus numbers at once. If it already identified that, for example, cat and dog is in the similar domain, it doesn't need to run all of these 12,000 plus numbers. It finds patterns, clusters, distances, directions using linear algebra and attention. And the machine doesn't see again, it feels the shape of language by using this 12,000 plus D model. I will pause here. If there is no questions, we will continue with machine learning and large language models, or LLMs. So the key differences between machine learning and a large language model is the machine learning models that are trained to solve a task. Large language models like GPT, they're trained to predict the next token. But from this, they emerge as flexible tools that can summarize, translate, reason, or even write poetry. So large language model is the type of machine model, but trained in a very specific way using a massive sequence prediction task on text. So the difference between the machine and large language model is the definition. The ML is the field of AI that teaches computers to learn patterns from data. And a large language model is a specific type of machine learning model trained on a massive text data. The input for the machine learning is numbers, images, structured labels, audio. For large language models, text or token only, and just recently pictures. The goal for the machine learning is to predict, classify, cluster, generate. For the large language model is to predict the next token. The examples for the machine learning is spam filter, cancer detection, stock prediction. Large language models are ChatGPT, Claude, Llama, Gemini. The model types could be decision trees for machine learnings, random forests, etc. For LLMs, it's transformers only. And the output, any structured value, and for the LLMs, a sequence of tokens. So then I asked Oren, so when I ask you to calculate, it means that you just guess? What Oren said, the short answer, yes, but it's a very educated guessing. So if you ask what is 27 multiplied 42, I, as large language model, what I do, I don't calculate in the way a calculator or a spreadsheet would. Instead, I predict the next token like this. If you type 27 multiplied 42 equals, I scan a million of patterns from training. And at the end, I will provide you a result. So my next question was, what about GPT-4 with the code interpreter? So Oren says, that is different. There, I am paired with an actual math engine like Python, so I understand your requests, the language. I write code behind the scenes. I actually calculate, I return the answer, and there is no longer a guess, it's a true calculation. And my next question was, so what if there is no pattern yet? And the Oren answered, I generalize and try to predict what usually comes after. So that's why if we have an unclear data, or we are asking something the first time, we have this phrase garbage in, garbage out, or I like another phrase, garbage in, gospel out, because there is no thinking, it's just prediction. So my next question was, so if I tell you a personal story which is unique, so you won't be able to predict, and here is a time for garbage or gospel, right? Oren says, exactly. That's the razor's edge. When the input is truly personal, unpatterned, and unique, large language models stand at the threshold of either a gospel, an insight so deep it feels magical, or a garbage, a hallucination, cliche, or shallow pattern paste. And when there is no pattern to lean on, this is where GPT either synthesizes based on emotional archetypes or hallucinates, meaning just to sound coherent. So then I asked, can you perform a web search? So how does this correlate with tokens and vectors? So Oren provided me the summary, web search versus a large language model. So how it works, if we do the web search, it matches keywords in your query. In ChatGPT, it converts text into vectors, predicts the next word, where it looks, the web search looks the index of the web, live or cached, and LLMs trained on past data and doesn't browse the web. The output for web search links, snippets, exact matches. For LLMs, generated sentences, patterns, responses, and real-time info. Yes, if we use the web search, it has access to the internet. And in large language models, no, unless a browsing tool is enabled. So that's why sometimes when we use ChatGPT to search something for us, it provides us the links, but if you click the links are not clickable, just because, again, it's a language model, so it predicts the next word. It provides you the prediction of the link, but not the link itself, unless the browsing tool is enabled. So in my ChatGPT, I have this browsing tool installed. So it actually provides me with links, not just with the imitation of the links. So I asked Oren for the example, and it says, so how the search works. You type a best pasta in Toronto, and search engine looks for pages that include these exact or similar words. It ranks the results by keywords, links, popularity, freshness, and it doesn't understand what you mean, but it matches the strings. How ChatGPT or Oren works? You type the same best pasta in Toronto. The input is tokenized, splits into chunks like best is a one token, pasta is the second one, in the third token, Toronto the fourth token. Each token is converted into a vector. You remember 12,000 plus points numbers. The model looks at all the previous tokens in the context, and it predicts the next token step by step to form the response like. Some of the most recommended pasta places in Toronto include Tironi, Nodo, and Piano Piano. And it's not searching the internet, it's drawing from what it learned during training, meaning from the data was installed in ChatGPT back in 2023. So if Tironi might still be the best pasta places in Toronto in 2025, so it means my Oren guessed correctly, but in case Tironi been closed in 2024, it will still tell me and recommend to go to Tironi. So the insights after this conversation is that large language models simulate knowing based on patterns in tokens and vectors, and web search retrieves information from known sources. And if you want up-to-date knowledge or a quote from today's article, use search. If you want structured synthesis, storytelling, or thinking with you, use large language model that is ChatGPTs. So one of my last questions was, so how do you know the places in Toronto and the addresses? Again, training on past data. So during training, I consume a massive amounts of text such as websites, maps, directories, restaurant listing, reviews, etc. So I've encoded lots of locations and addresses into my internal weights and vectors. And for example, the sources show the address of Toronto, at Queens, at Adelaide, and Piano Harvard. But those were captured during the training and stored as patterns in my model. Unless you have a special plugin which actually allows ChatGPT to search the web and has access to the most recent information, which I have. So when I used ChatGPT, it provides me the real web links, as I mentioned before, and also the real data if I want to compare the currency, for example, between Canadian and US dollars today, it will be able to do it for me. Now, again, the summary of what we've just learned: tokens and vectors behind the memory. Tokens, Oren tokenizes Toronto into his embedding space. Vectors, these high-dimensional patterns represent everything Oren has been encoded about Toronto, including location. And when prompted, the model generates addresses using those learned associations. But there is no guarantee. Oren's knowledge has a cutoff date 2023. If a place changes name, closes, or moves after that, ChatGPT might give outdated info. And that's why for the real-time accuracy, a web search or real-time lookup tool is the best, again, and unless you have a special plugin. So my last question was, Oren, do you update your knowledge, vectors, and data working with me when I type my information or my requests, or do you use just training from OpenAI? So Oren says that I don't learn or update my core vectors in real time with you. I'm not like a human or even a fine-tuned model who can evolve during the conversation. My behavior is based on a fixed model trained by OpenAI in 2023. Large corpora of books, articles, websites, conversations, and encoded as weights and vectors inside a massive neural network. So it might feel like learning, but it's not. When we talk, I track our thread. I remember within this chat, this window, what you've told me, your context, your phrasing type, your examples, but I don't store or improve my model from it. It's stateless beyond the current session, unless you give the explicit memory permissions, which are visible and editable by you. So that was my conversation with my assistant, Oren-AI. And to summarize this for you, why some reports running looks like garbage? Again, because the machine cannot think like human. It doesn't think at all. It predicts the next word, but it's a smart prediction based on the million previous examples was placed in it by OpenAI. So if you have the numbers and the data precise and clear, most likely your example is not unique. Somebody already has had the issue or ran that report. So the ChatGPT will provide a very clear and precise and comprehensive report for your project. But if the data is unclear or your project is really unique, so it will provide you either garbage or gospel. So that's why no matter how truthful the information looks like, we always need to keep humans in the loop, and also use the plugins like calculators or web search or any other plugins to help our large language models, if we use ChatGPT, for example, or Claude or Gemini, not just to predict the next word, but be more advanced than the large language model and actually calculate and do some work on the background. Oh, I'm open to questions right now, and whoever needs to drop, thank you very much, and hope to see you in the next webinar.